Okay, so good day, everyone, wherever you are. Welcome to the LieJor seminar in São Paulo. So today we have two seminars. First one is now, and the second one is in the usual time at 14 hours, São Paulo time. Ivan is having technical difficulties today, so I will be in charge. And it is my great pleasure to announce our first speaker today, Kang Seok-Jin from the Korean Research Institute of Arts and Mathematics from Asan, Korea. So it's a pleasure to have him here. He's an old friend and colleague, and he will speak on quantum Borcherds-Bozec algebras and abstract crystals. Please.
Okay, thank you very much. And it is my pleasure to be able to speak in the seminar at São Paulo. I remember I visited there in 2008. So I still remember the beach where there was a lot of rain. So we did not enjoy too much at the beach, but I enjoyed the experience in São Paulo. So let me start. My subject of this talk is quantum Borcherds-Bozec algebras and abstract crystals. So what are quantum Borcherds-Bozec algebras? Let me start from the beginning. So let us begin with Cartan datum. Okay, for the Cartan datum, this is for finite dimensional simple Lie algebras. We begin with finite index set and a square matrix called symmetrizable if there is a diagonal matrix which makes D symmetric, asymmetric. Then Cartan matrix satisfies the following conditions. All the diagonal entities are 2 and non-diagonal entities are non-positive. Okay. And furthermore, we add the condition that A is positive definite. Okay. Then for the Cartan matrix or Cartan datum consists of a symmetrizable Cartan matrix, as I described above, and it consists of a free abelian group P, which is called the weight lattice, and the set of simple roots, and the P check. I just forgot how to call it. So P check, the dual weight lattice, and pi check, the set of simple chords. We expect they satisfy the following conditions. First, the pairing between Hi and alpha j gives the entries of Cartan matrix. And since this is positive definite, A is a positive definite, and it naturally comes that pi is linearly independent over Z. Then for each I, there is an element lambda I, which is called the fundamental weight, such that the pairing with Hi is determined by the Kronecker delta. Okay. Then, given a Cartan datum, we can associate the Lie algebra G such that G is finite dimensional semi-simple Lie algebras and all the roots are real. That means their norms or the lengths are positive. Moreover, all the root spaces have dimension 1. And these Lie algebras have a presentation given by set, which are called the set relations. And we can associate a quantum deformation of G, but I will discuss this later. Just next page. Then we would like to generalize the notion of Cartan matrices. So still I is a finite index set, and a square matrix is called the generalized Cartan matrix if still the diagonal entities are 2 and off-diagonal entries are non-positive, and A is symmetrizable. But here, we do not require that A is positive. And this datum, I would call it Katz-Moody datum. And in Katz's book or Moody's paper, they used generalized Cartan matrix. But I would just say this is Katz-Moody Cartan matrix. And again, as before, we have weight lattice, simple roots, dual weight lattice, and simple co-roots. So we do not require that A is positive definite. So to make pi is linearly independent, we need some elements in the Ham space and dual weight lattice, etc. So still the pairing gives the entries of A, and for each I, we still would like to have an element lambda I, whose pairing with HI is given by Kronecker delta I. Okay. Then, given the Katz-Moody Cartan datum, we can associate a Lie algebra G such that G is usually infinite datum, infinite dimensional, and all the simple roots are real. That is, their norms are positive. But so simple roots means alpha i's. They are real, but there are imaginary roots. That is, there are roots whose norms can be non-positive. And typical example is, so given a Katz-Moody Cartan datum, we can associate Lie algebras, which are called Katz-Moody algebras, well, since about now 40 years ago. And very good typical example is affine Lie algebras. And they have a lot of important applications in number theory, combinatorics, and mathematical physics, etc. Then for weight lattice P, we define the set of dominant integral weights whose pairing with lambda is always non-negative. And we will denote by R the free abelian group with basis consisting of simple roots. And we will denote by R plus the set of which consists of non-negative linear combination of simple roots. And then for an element of R plus, we'll define the height of beta for the sum of ki's. Okay. This is rather typical notation for Katz-Moody algebras. From my experience, if I give an online talk, it goes very fast. So let me take time. Now, what is the differential quantum group, which should be called quantum Katz-Moody algebra? And we denote by U sub QG usually. That is the associative algebra of QQ over with the identity element 1 generated by the element Q to the H. Here, H runs over dual weight lattice, and the symbols EIs and FIs, which usually correspond to simple root vectors, simple roots, and with the following defining relations. So here, Q0 is 1, and QH and QH prime are commuting with each other. And this is the formation of the relations that H is acts as a diagonal element. Now I can do it. So, and Q to the H act as a diagonal operators on E sub j and F sub j's. And moreover, in the algebra case, we have the relations that EI and FJ almost commute each other. But now its quantum deformation is this relation. This is the quantum deformation of the relation. Here, K sub I is Q to the I HI. Now, I did not tell anything about I, but to define the symmetrizable matrix, we use a diagonal matrix D. So D is diagonal entries DI. So here, QI is Q to the DI. So this is the definition of KI. Okay. Now, so this is quantum set relations. Usually, actually, this is same as set relations. If we just understand this as a user combinatorics, okay, user binomial coefficients, then this is definition, relation for user Kac-Moody algebras, which is called set relations. So quantum group is defined by Q to the H, EI, FI, and with these relations. So this is quite standard for quantum Kac-Moody algebras. Now let us move on to Borcherds algebras. So here we take I, the index set which can be countably infinite, and now the square matrix A is called the symmetrizable Borcherds-Cartan matrix. So instead of Kac-Moody Cartan matrix, I use Borcherds-Cartan matrix. Here, difference with the generalized Cartan matrix is that the diagonal entries can be non-positive, even integral numbers, even integers. Of course, we can define for just the non-positive integers, or even for non-positive real numbers, but just for convenience, I took the non-positive even integers. Also, the negative off-diagonal parts are non-positive, and A is symmetrizable. Now, let me just, I don't know how to erase everything once, but of course, moreover, that's dangerous. So let me use this way. So that I would denote by real indices if diagonal entities are 2. And I would denote by imaginary indices, the set of imaginary indices where the diagonal entries are non-positive integers. So here, in this part, are called imaginary indices. But among them, when diagonal entities are 0, then the things are rather peculiar. So we would denote by isotropic. Okay. Then here, Borcherds-Cartan datum is almost the same as Kac-Moody Cartan datum or Cartan datum. So it consists of symmetrizable Borcherds-Cartan matrix. So again, the Borcherds-Cartan matrix allow that their diagonal entries are non-positive integers. And then everything else is the same. So we have free abelian group, which is called the weight lattice. We have the set of simple roots. we have the linear space, which is called the dual, well, just free abelian group, which is called the dual weight lattice. And we have the simple co-root, whose pairing with alpha j, the simple root, gives the entries of generalized Cartan matrix. I mean, Borcherds Cartan matrix. Borcherds Cartan matrix. And we also require that pi is linearly dependent. In that sense, we need to extend the weight lattice. So it follows that the dual weight lattice also needs to be extended. And also, we would like to have fundamental weights lambda. Okay? Then, given the Borcherds Cartan data, we can associate Lie algebra G such that there can be imaginary simple roots. Okay? So in Kac-Moody case, there are imaginary roots, but in Kac-Moody case, at least simple roots are real. But in Borcherds case, we allow that imaginary the simple roots can be imaginary. But still, the simple roots have degree 1. I will explain later, but we only allow alpha I to be called the simple roots. So they are the simple roots, no other roots can be called simple roots. And the Lie algebras associate with these Borcherds Cartan data are called Borcherds algebras. And in many references, they are called generalized Kac-Moody algebras. But to make it clear, I'd rather use Borcherds algebras. Okay. Then, the defining relations for quantum Borcherds algebra is almost similar to the quantum Kac-Moody algebras. Here, Q to the H acts as commutative abelian group, and Q to the H acts on EIs and FJs as diagonalizable operators. Then here, EI, FJ, FJ, EI, their commutation relations is almost the same as quantum Kac-Moody algebras. Now, the difference is that quantum set relations are defined for real roots only. So for those roots whose norms are positive, that's real roots. And J should be different from, of course, J. Still, recall that Kac-Moody case, all the simple roots are real. So we don't have to write I real here, but the Kac-Moody quantum Borcherds algebra case, simple roots can be imaginary. So we only require the quantum set relations for real simple roots. And also we need more relations for generators. So when the entries of Borcherds Cartan matrix is 0, then we require that EI, EJ commute with EJ, EI, and same is true for FI, FJs. Now, but I really want to talk about the object that I would like to talk about is quantum Borcherds-Bozec algebras. So this is important, but I did not make it important. Here, this index set is I infinite. So it consists of I for I real. And then we take the pairing between I and positive integers. Okay? I usually make the same mistake. I somehow begin with I just think there are enough spaces, but somehow there is no enough space. Anyway, still, the set of I infinite consists of real indices and also the pair of imaginary simple index and positive integer L. Then what is quantum Borcherds-Bozec algebra? As I told Slava that maybe even Borcherds and Bozec, they do not know their names are used for the definition of this algebra. But anyhow, well, Bozec used generalized quantum group. So I think it is better to use quantum Borcherds-Bozec algebra because it is associated with the Borcherds-Cartan datum. That is, this algebra is associated with the Borcherds-Cartan datum. So same datum for Borcherds algebras, but it has more generators. So here we have more generators here. So QTH is the same as Borcherds case, but we have more generators for each indices for I infinity. And their defined relations are similar, but we should not miss important things. So their commutation relations is here. We have pairing. Okay. So when H is HI, then we would have Q to the I L Aij instead of this. Okay. So this is different from quantum Borcherds algebras. Also, if I is different from J, as it's written here, then those defined relations, they commute each other. The generators commute each other. Okay. But the problem or interesting or complicated thing is the commutation relation between EIJ and I would want to write EIK, any EIL or FIJ, FIL. So in Borcherds case, so EIFJ minus FJ EI is given in a rather simple way. But here, the defined relations are quite complicated. Not sure whether. Also here, as is Borcherds cases, the quantum set relations are defined for real indices only. Okay. Then here, the only difference is L. Okay. But I would say the really difficult thing is this part. And as it is quantum group case, the quantum Borcherds-Bozec algebras are can be constructed in using the Dirichlet double process. So like we take non-positive part and non-negative part, we take the tensor product, then there are too much space for Cartan part or U0 part. So we need to factor out by some relations. And this part is those relations for double part. I mean, which arise from quantum Dirichlet double process. So that's why it is rather complicated. And it is actually more complicated, but we can reduce down that complicated things using 700 Vandenberg construction. Okay. Now, what is the representation theory? It is very similar and similar to Borcherds' case. So I will just skip this part. And I would say we can define the notion of highest weight module. And we will mostly concentrate on irreducible highest weight module with highest weight, with dominant integral highest weight. Okay. Now, I will just skip this part. What I would like to give you is an expression for the characters. But anyway, I will just skip. So here, Bozec, Schiffman, and Basserot gave the character formula for the irreducible highest weight modules over quantum Borcherds-Bozec algebras. And I will not explain this. Okay. And when lambda is 0, we will obtain the denominator identity, and it can be used to determine the root multiplices for Borcherds-Bozec algebras, which is the definition to quiz 1 case, classical limited case. But anyhow, it's not today's topic, so let me skip. The only thing is we can define the notion of category O integrable, and it is semi-simple, and all the simple object is given by the irreducible highest weight modules. And I will just skip. Now, where Bozec defined the crystal-based theory, which is generalization of, I don't know, Kashiwara's crystal theory, or Lustig theory. I don't know. Or here I can write canonical basis. Okay. Now, well, Bozec also gave the notion of generalized crystals, but I would introduce a simpler, more simple version of his generalized crystal, and he would call his generalized crystal an abstract crystal, but I would just call my abstract crystal the abstract crystal. Sorry, like redundant expression. So here, the notion of abstract crystal So what is abstract crystal? As I said, B, and with the maps weight and casual operators and the functions epsilon I, phi I, which is mapped toward integers and just to some symbol which is called negative infinity. And this is rather special, rather standard properties. So if you take a weight of EI tilde IL, so recall that casual crystal or Rustic theory, we usually have at least one only. So for Kac-Moody case or Borcherds algebra case, we always assume L is 1. So, but here L can be bigger than or equal to 1. So we need to define the casual operators for L bigger than, so L bigger than 2. And in this case, weight is increased by L and decreased by L. Here I forgot to mention that EIL are generators. They are generators, and their degrees is L alpha I. So in that sense, for this L, generators can have higher degree. In Kac-Moody case or Borcherds case, degree of EI is just alpha I. But in Borcherds-Bozec case, we have a lot more generators because we have all positive integers. Generators for, I'm sorry, I think I'm getting sleepy because it's night. But since I'm a night person, I should be awake. Sorry. Anyhow, so in Borcherds-Bozec case, we have a lot more generators where compared with the Kac-Moody case or Borcherds algebra case. So a lot more generators and they have a higher degree. That's the main difference. But still, we need to have this case. And then EI E tilde IL and F tilde IL, they are almost inverses to each other. And also here, so epsilon I are decreased by 1 and increased by 1. Epsilon I is increased by 1 when we when we apply EI tilde, and phi I is increased by 1 when we apply EI tilde. The same case here. But note that we only use here. Okay, that's typical with the Kac-Moody case or Borcherds case. So this is same as Kac-Moody case and Borcherds case. But for imaginary case, so Borcherds-Bozec case, in this case, we take this assumption. So here, epsilon I is not increased or decreases. Okay, here, compare with this, epsilon I is decreased by 1 when we apply EI tilde. Phi I is increased by 1 when we apply EI tilde. And same for here. So depending on whether we apply Fi tilde or EI tilde. But in this case, at least epsilon I are not changed. they just stay the same. Then phi I are defined in the following way. So phi I, I'm sorry. So phi I actually they are defined in this way. Here epsilon I they just stay the same. Then phi I would be defined by this value. Okay. Now when in Bozec's paper he just used another definition, and I would say this simplified version makes everything simpler. So I think only difference, or not only, but the crucial difference is this definition compared with his case. Well, typical example is Borcherds-Bozec's crystal basis. So when I is real, then that is same as Kashiwara case. And when I is imaginary, non-isotropic, and here C is composition, then we can have decomposition of any element in quantum Borcherds-Bozec algebra. Then in this case, we can use the Kashiwara operators. We can define the Kashiwara operators using special generators. I mean, they are not EILs or FILs, but there are other generators which can be called primitive generators. Okay, but I will not spend too much time on this. But at least for isotropic case, things becomes a little bit more complicated, but not really complicated. And so we need to expand the defining field, say QQ to, Q to, we need to extend to something F, which contains all the necessary square roots. But still, one can develop the crystal-based theory following Bozec's examples of Bozec's standard argument. But now, so I would give an example for abstract crystal. Now, usually we take localization of rational functions, well, actually, the functions, regular functions at Q is 0, so localization of FQ when Q is 0, and L infinity is A0 submodule of UQ minus G, spanned by the old elements of the form. So you apply Kashiwara operators on 1 as much as you want, then take the A0 submodule. And B infinity, again, you apply Kashiwara operators as much as you can and take the modular QL infinity. Then, so for this element, we just define the weight as we expect. So the weight is 0. And if we take FIR, LR, then this weight is alpha IR, LIR, alpha IR. So, so from here, we would say L1 alpha I1. Then here, LR alpha IR. So the weight will be this. But important thing is here. So usually for real indices, you define epsilon IB to be the maximum of EI tilde K becomes non-zero. That means if you take crystal graph, and if you have B, then epsilon IB is number of errors coming here. So here epsilon IB is 3. Okay. So in this case, I'm sorry, epsilon IB is 3. Then phi I is defined here. Then actually in this case, phi I is B. I'm sorry, phi I is B is 2. But when I is imaginary, we define epsilon I to be 0, which makes everything quite simple. But still, phi IB is defined by these relations. So for any I, so when I is imaginary, this is 0. So phi IB becomes the same as the pairing of HI with weight of B. Then with this definition, so that means we have So we have here. Okay, we have Casual operators, and we have Casual operators here too. And we have weight and epsilon I, phi I. With these 5 functions, the set B infinity would become an abstract crystal. And why is it important? Because it would describe the crystal structure on UQ minus G. Then it would describe the combinatorial features of UQ minus G for quantum Borcherds-Bozec algebras. Okay, for the irreducible high-to-weight module, Bozec also defined the notion of EI tilde, EIL tilde, and FIL tilde. Then weight can be defined from lambda minus Li alpha I k, Lk alpha I k, and others are almost the same. So if some I is 0, the only important thing is 0 when I is imaginary. Okay. Okay. Let me just skip. As I said, they are similar to B infinity. Then B lambda becomes an abstract crystal. So now, again, let me just here B lambda would explain or describe the combinatorial structure of B lambda. As I said, B infinity would describe the combinatorial structure of UQ minus G. So we can understand their structures using the crystal operators. Now, there is special crystal which are called elementary crystals. So in real case, so we fix I, then we define the elementary crystal Bi, and their elements are just L. Okay, and for each non-negative integers, and we define the weight epsilon I, phi I, and crystal operators in the following way. Okay, but point is the weight is minus L alpha. Okay. Then the crystal structure is given here. Okay. So for each non-negative integers, the crystal structure is this. Okay. For real indices. But now, how about the imaginary indices? Here, when I is an imaginary index, but which is not an isotropic, so here AII is just a negative. Okay, so AII is not zero. Then the element is here. Okay, just composition. Okay, so for given composition, we define the weight to be the length of composition and alpha I, because it is determined by I. All right, and this is a special crystal structure. I mean, these special functions define the crystal structure on BI, and their crystal graph is given here. Okay, so it is defined by compositions. If you forget i's, I mean, just consider I and 2, 1, 2, 2, those things, then we get compositions, right? So I do not know how to make the graph very well, but anyway, this is composition of 2, I mean 2, again this is 2, and this is 3. I'm sorry, I don't know where it becomes 3. Okay, yes, 3, right? Somewhere we can find 3 too. All right, so crystal graph for BI is given by compositions, but the elementary crystal for isotropic roots, then their structure, I mean their elements, its elements consist of partitions. Okay, to save the time, let me just give the structure of crystal graph of elementary crystal. So they are determined by partitions, and then its graph is better. So I don't know where, I mean, you have 3, there should be some 1, 1, 1 hidden. I mean, I just cannot find. So I mean, they consist of partitions. Okay, they are arrows, not elements. Don't be confused with the elements. They are arrows. Okay, so their elements are here. Okay, so again, we have the notion of elementary crystals. They play a crucial role, actually, crucial role. Now, I will not describe the structure of a tensor product of abstract crystals, but it is rather natural if we use the notion of epsilon i's in our case. So here, when I is imaginary, epsilon I is 0. So that simplified version becomes everything simpler. So, I mean, I will just skip this part. Then, this is what I would like to. This is the main subject of my talk. So, I mean, what can I do? Previous page. So here we define notion of quantum Borcherds-Bozec algebras, and then high-state module, and crystal graph B infinity, crystal graph B lambda, and here UQG. So it describes the combinatorial structure of UQ minus G, and it describes combinatorial structure of B lambda. We have elementary crystal. So we will just combine them together together with tensor product rule. I didn't describe the tensor product rule here, but it is important, but I did not do it. Now, what is crystal embedding theorem? Well, we have crystal embedding comes from B infinity to the tensor product of B infinity to Bi, which is the crystal embedding theorem. What does it mean? So take an infinite series sequence such that every index appears finite many times. For example, 1, 2, 1, 2, 3, 1, 2, 3, 4, etc. Okay, and we just define an infinity, the tensor product of elementary crystals corresponding to each sequence. Okay? Then, using this crystal embedding theorem, we can apply this crystal embedding theorem repeatedly. So first we have this sequence. And then recall here I is I1, I2, etc. So define another crystal embedding theorem, another crystal embedding theorem, etc. Then we have crystal embedding theorem for P infinity. I2 tensor P I1. Then P infinity is isomorphic to the connected component of Bi, P sub I, containing the element here. Okay. Okay. So this is important. So P infinity is contained to, I would say, so P I1 tensor P I2 tensor, etc. Then it corresponds to connected components of this element. Okay. Then this is the main result. Okay. Suppose we have an abstract crystal, and suppose we have an element in P0 such that weight is 0. And suppose we have, this is the unique element which is annihilated by EILs. This is a unique element. And suppose we have crystal embedding, then this B is isomorphic to P infinity. Okay. The proof, the idea of proof is that we apply crystal embedding theorem repeatedly, then B is isomorphic to the connected component of Bi containing the element here. So which implies that B is connected component of, B is isomorphic to B infinity because B is connected component of here and B infinity is connected component of this one corresponding or containing this element. Okay, containing this element. Sorry, I'm in a hurry because the time is up. And then again, we can describe the crystal B lambda in an abstract way. So we have abstract description of B infinity and B lambda. Why are they important? Bozec gave a geometric realization of P infinity and P lambda using the Lustig's quiver varieties and Nakajima's quiver varieties. And we can reproduce his construction using this notion of abstract crystals. Of course, he already gave the constructions, but I'm sure that our construction, our characterization is simpler. Construction is the same, but characterization is simpler. And for quantum Borcherds-Bozec algebras, one can develop perfect basic theory and dual perfect basic theory, which are on the way with the joint work with Fan, Kim, and Tong. So they are Chinese, he's a Korean, and I'm a Korean too. But anyhow, so when we define for perfect basis and dual perfect basis, you can define a graph, but we have different perfect bases and different dual perfect bases for the same modules and for the same algebra, but their graph structure is isomorphic. All their graph structures are isomorphic to P lambda, P infinity and P lambda. Well, to prove that, we can use this construction. And also, important and interesting thing is categorification of quantum Borcherds-Bozec algebras and their high-to-it modules. And well, in our construction of, in our means Kashara, myself, and my students, construction of quantum Kac-Moody superalgebras, even quantum Kac-Moody algebras, we used perfect basis theory. We could have used perfect basis theory for quantum Kac-Moody case, and we used perfect basis theory for quantum Kac-Moody superalgebra case. So in the same spirit, our theory, these abstract crystals, will play a crucial role in the categorification of quantum Borcherds-Bozec algebras. We have not done yet because we are defining quantum Komanov-Lauder-Rookie algebras for the case AI0, and this is somehow rather complicated or simpler because we deal with the partitions, but again, that makes things simple and complicated. So now our theory can be applied this object and other things. So I think this is basic for fundamental facts about the theory of quantum Borcherds-Bozec algebras. This is it. Thank you very much.
Thank you very much, Seok-Jin.
So shall I go back or what shall I do?
No, yeah, you can appear now. Well, let's thank Seok-Jin.
I don't know what to say. Where am I? What can I do?
Click on click on your picture.
Okay, maybe I can appear. So at least there are many people.
Just open camera.
Anyhow, you cannot see me. I cannot see myself, but it's okay.
Okay, so are there any questions, please? Yeah. So there was a one raised hand. Andrew, do you want to ask something? No?
No, not right now.
Okay,
good.
I have a question, Seok-Jin.
Yes.
So the main result gives a characterization of the crystal, a different characterization of the crystal, which might be useful in the categorification and so on and so forth, right? For Borcherds-Bozec quantum algebras. What about the classical case? In the Kosmody case,
this is the same.
right?
Yes, we take L is 1, and we can reduce everything down. So when L is 1, it would give the abstract crystal structure for Borcherds algebra case. And if we just take off the condition for imaginary indices, then we recover Kac-Moody crystals. Yes.
Okay. And the highest weight module with integral dominant highest weight, is it integrable in the direction of simple imaginary root?
Oh yes, for the simple real roots, it's integrable, and even for simple imaginary roots, it's integrable in the sense that it will be annihilated by EILs for finite many times, but for Fi, it's never integrable in the sense that if you apply Fi's, then it can be applied for infinite many times, like in Borcherds' case.
Right,
it's
right.
Not the same. It's not the same in Kac-Moody case, but Borcherds' case or quantum Borcherds-Bozec case. Fi or FILs can be applied infinite many times.
In particular, it is always infinite dimensional.
It's always infinite dimension, yes.
And one more naive question. In the definition of the Borcherds datum,
Borcherds-Cartan datum, yes.
Right. So you allow even negative integers, right?
Yes.
And why not positive? Why cannot you go to the left?
For actually, what can I say? We don't need, in some sense, because for real indices, we don't need. But I still remember for Peter Slodowski's construction, he did not assume AIs too. He assumed the AIs can be any positive integers, and I never understood his construction. But I looked at when I was graduate student, which is already many years ago. I don't want to say when it was, but I did not understand his construction at that time.
Okay, but there is still a room, right, for generalization.
Yes.
Okay. Thank you, Seok-Jin. Any other questions or comments? Well, if this is not the case, let's thank Seok-Jin again for a very enlightening talk in this very late hour in Korea. So thank you very much.
Okay, thank you very much, and thank you for your attendance. There are many more people than I expected. So thanks a lot.
Thank you, Seok-Jin. It was wonderful to have you with us.
Okay, thanks a lot.
So I would like to remind everyone that we have a second talk today at 14 hours. So, and the speaker will be Vladimir Bavula from UK, from Sheffield. Okay. Thanks everyone for participation.
Okay, now I can see you. All right. Okay.
Okay.
Thanks a lot.
Okay, so see you at 2.
Okay.
Thanks a lot, Seok-Jin.